We're going to go to Newton's first law. Now, here's Newton's first law. Guys, it's going to be asked, right? You must be able to say this in your sleep. A body continues in a state of rest or uniform motion in a straight line unless acted upon by a resultant force. Okay? Things don't do this because Newton said it. Things do this, and Newton observed it. And he was the first person to kind of state it properly. All right? Yeah. So this describes inertia, right? A body continues in a state of rest or uniform motion in a straight line unless it's acted on by a resultant force. Now, there's a very nice way to demonstrate this. If you take a beaker or glass and you put it on a piece of paper, obviously, if I pull a piece of paper, the beaker moves with it. But you've seen those things where they snatch it out underneath and the glass stays behind. Now, you think it could work?
Yeah, I think so. Full down. No, sir. Full down. It's too light. No, just full down.
My kung fu is coming in.
Why are you clapping?
But actually, if you get clever. Now, let's up the ante a bit.
No, so you can't. I say impossible.
No, you can. You definitely can. It makes it easier.
Makes it easier.
No, let me just say.
I think it makes it easier.
It makes again. No, it's the more weight, the harder because it's the put it.
It's easier.
David, you wanted to try?
Oh no!
Are there consequences if it falls off? Yeah, it smashes. Actually, I'll be honest. I think it's more weight, more stable it is.
I owe this worse.
Right, so why does it stay standing still? What's that called?
Friction.
Well, friction is this. Why is it standing still? Inertia. What's inertia? It's the tendency of a body to remain in a position of motion or standing still. Obviously, why doesn't it move when I do this? Why does the paper bend? Because it doesn't want to move. Okay, it's got inertia. Inertia is basically Newton's first law. Newton's first law describes inertia. Most objects will stand still unless they are pushed, and if they're being moved, they'll want to carry on moving. Now, if you get this thing moving and then try it, it's much harder. Because once it's moving, it wants to carry on moving. Now, not that it knows what it's doing, but that's what happens. Okay? So, Newton's first law is what? Say it. Say it loud to yourself.
A body.
A body will continue in the state of rest or uniform motion in a straight line unless it's acted on by a resultant force. That's Newton's law in pictures. I've demonstrated it, and that's it in words. All right? From today, you must know Newton's law out of your head. Okay? You must be able to quote it. I guarantee you it's going to be asked in at least one test or an exam. I'm telling you what's in your exam before you even get the exam paper, right? That will be asked. So I'm trying to represent it here in pictures. The law describes inertia. You can see this object here is moving with a constant velocity, and it tends to want to carry on doing that. Okay? So if things move in a constant velocity, they will want to carry on doing that, or if they're standing still, they want to carry on doing that. If there are balanced forces, it tells you there, in the event of balanced forces, Newton's first law applies. but only when there are balanced forces. Okay. For example, if I lift this thing up slowly, why is it going up slowly? Because my force is cancelling out its weight. And that's why it will carry on moving. All right. Only when the forces are balanced. So there's Newton's first law. Now, obviously, you've probably seen this one as well. If you've got, a card or something on top of a beaker, and you flick the card out underneath, then whatever was on it will drop into the beaker. Okay, little party trick that you can do in a pub or something. So again, that thing was standing still because the card was moved quick. The friction wasn't enough to overcome the inertia, so it will carry on standing still. Now, gravity. You've got the Earth and you've got the Moon. You know that the Moon goes around the Earth. Yeah? In a circle. Now, is the Moon moving with a constant velocity?
Yes.
Kind of. It's kind of like this. If I swing this thing around, ideally I'd like a ball on the string, but I haven't got a ball, so Josh, if I swing this thing around, okay, is it moving with constant velocity? No. Is it moving with constant speed?
Yes.
Yes. So it's moving with constant speed. It's covering the same amount of ground of distance every second, but its direction is changing. So it's not moving with constant velocity, it's moving with constant speed. Why? Why is it moving with constant speed? Why is it moving? I'm swinging it around. Which direction can I pull it? With a cord, you can only pull in one direction, towards the middle. The way I move it in a circle is by doing this. I keep moving my hand in a circle. Because my hand's moving in a big circle, it moves in a big circle. But I'm only pulling it towards my hand. I can't exert any other force with a rope. You can only pull it in one direction. But because my hand's moving in a big circle, now it moves in a big circle. When you move it, my hand's still moving in a circle. Right? So the force, the only force on this thing is in what direction? Towards the middle. Now it's exactly the same as the moon. Watch this picture of the moon. Where does the moon come from? Comes from somewhere. And it gets trapped by the Earth's gravity. It's the same as if you were running down the pavement and you stuck your hand out next to and you grabbed a lamppost. What would happen? You spin around. That's exactly what happened to the moon. The moon was moving past the Earth really fast because of the Big Bang, and it got trapped by the Earth's gravity, and now it spins around it. And the only force on the moon is in what direction? Towards the center of the Earth. The moon is actually falling towards the center of the Earth all the time.
So is gravity never constant?
Yes.
It's never changed?
No. So let me show you something else.
Why would gravity change from another planet?
Let me show you something else. Watch this. Watch this. Hang on.
Gravity is not constant throughout the universe.
Hang on.
Yeah, I'm pretty sure that
In the around the Earth it is. Watch this. Let's say you we're standing. Let's say here's the Earth, okay, and here's a mountain, and you standing on the mountain, and you decide, sorry, you want to throw something, all right? You throw it and it falls towards the Earth. And now you throw harder. Now you throw even harder. So it misses the Earth. What happens?
Hits you in the back of the head.
Hits you in the back of the head. You've now put it into orbit. Question is, who threw the moon?
Big Bang.
The Big Bang.
So it didn't come off Earth?
The Big Bang. The Big Bang exploded everything. Everything was moving past everything else. The moon came past the Earth, got trapped by the Earth's gravity.
So wouldn't everything be more, if you like, in the center of the Earth? It will be the same.
Same. No, it gets smaller as you get towards the center. Yes. It's not. No. Same distance. So the moon moves around the Earth in circular orbit. Explain why. That's because it's being pulled towards the center by gravity. And what I've done here is I've left you a few things to write out. A body has a natural tendency to resist any changes in its motion. This is known as inertia. If the card in this picture is flicked, then the coin will drop into the beaker. That's because the friction between the card and the coin isn't enough to overcome the friction. Inertia would keep the peg stationary. Then you've got the moon moving past the Earth, getting trapped by the Earth's gravity. Gravity does not act in the direction of motion, but gravity acts towards the center of the Earth. And the only force on the moon is gravity. Now, David, you're doing your staring thing again. You're staring out into space, but I don't know what's happening on there.
Just trying to see the moon.
All right. So there's a few little things for you to fill in. All the things that are missing. Here's another slide. Yeah. Right, so you must be able to say Newton's first law. Okay. Now, we've discussed the normal reaction force. Okay. Up until now, we've said the normal force is the force that the surface pushes up with when you exert a force down on it. So obviously, if you put an object on a table, then the object pushes down on the table because of its weight, and the table therefore pushes back up on the object. You guys agree with that? Now, yeah, I've got a thing that can represent a table. If I put something on this, you can see this is quite heavy. Pushes down in the middle, and you can see the piece of wood is pushing back up. If the piece of wood wasn't strong enough, what would happen? It would snap.
So what do you mean
Okay.
it pushes up? Like,
Well, it pushes up. If I push down on this, it pushes back up on me. See? So, now what happens if I turn this at an angle? So I turn this. Which way is the normal force now? It's 90 degrees to the surface. So the normal force is now in that direction. All right. Whatever angle that moves, the same angle this normal force moves. Yeah. So there's your normal force in the one picture, and there's your normal force in the other one. All right. In this one here, the normal force and the weight are equal and opposite. So we'd say the normal is equal to minus the force of gravity. In this one on the right, what force or what component of force is going to give you the normal? Come on, you've done components. Which component is going to be equal to the normal? Perpendicular. So in this case, you know that the force of gravity is just mass times g. And if this was a 2 kilogram object, then you'd have 2 times 9.8, which would be minus 19.6. Because I've said here, calculate the normal force in each example if the ball has a 2 kilogram mass. Right? So if that's 2 kilograms, then the normal is minus 19.6. What would the normal force be here? See if you can work it out. If this ball was 2 kilograms and it wasn't moving, work out the perpendicular component. What's the formula going to be for the perpendicular component? Sorry, what about cos? So what would the perpendicular component be? Isn't f cos theta? Fg cos theta, because that's Fg, and your perpendicular component is the hypotenuse times cos theta. So your perpendicular component is Fg cos theta. We've already worked out Fg, it's 2 times 9.8. Now, if that's a 30-degree angle, cos of 30 is how much? Come, guys. So your normal is now minus the force perpendicular. Gents, I don't appreciate this. Your normal force is now minus the force perpendicular. Force perpendicular is Fg cos theta. So you've got Fg cos theta is 1.9 cos 30. 1.9 cos 30 works out to be 16.97. And so that's going to be your normal force. 16.97 up. You must be able to do these for slopes and for normal forces on a table. Okay, you've got to be able to work out the normal force. Now, all right, so now we've discussed friction. We said there's basically two types. You've got static friction and you've got kinetic friction. Kinetic friction when it's moving with constant velocity. Static is when it's standing still. In either case, you get the friction by the maximum force. In static friction, it's the maximum force before it starts moving. In kinetic friction, it's the force required to keep it moving with a constant velocity. There's nothing new on that page. We've done that all already. I haven't got time for nonsense. At the end of the lesson, before you leave, please make sure you hand in your friction pracs so I can mark those.
So because we're only in one pair graph. So
as long as I've got one graph with each prac, it's fine.
You said like 2 graphs for each group. Like,
Yeah. So
line
one graph
away.
with each prac.
Yeah.
Right. So coefficient of friction. Again, this is not new. You were doing this. It was a bit slow. It's because you're messing about. All right, can we go?
yes.
So static friction, we said with coefficient, the coefficient times the normal gives you the force of static friction. Dynamic friction, it's exactly the same format. This is what you're using with your prac, so there's nothing new there. I'm just showing you the equations. You should be filling in stuff, either on paper or typing. And I shouldn't have to tell you that.
So is the coefficient of
Yeah, so this extra bit says it depends on how it says.
Yeah, it might come. Extra bit?
Coefficient of kinetic friction.
Underneath that dynamic friction thing, it says coefficient of friction.
Dynamic.
Well, it's there. I've done it in red. The UK or UD is FK over N. You just take this one and paste it there and change the F.
What friction is this?
Kinetic. Yeah. UK is kinetic friction. Or you can call it D for dynamic. Kinetic or dynamic, either one. So that's just all the equations. You've used them all for your prac. So there's nothing new there. All right, can we go? So here we've got an example. If you had a smooth surface, fairly smooth surface, then a small mass like this, 0.1 kilograms. If it had a force of friction of 1 Newton, the coefficient of friction would be the force of friction divided by the normal. The normal would just be 9.8 times the mass. If the force of friction was 1 Newton, you'd have 1 over that, and 9.8 times that gives you 1. So your coefficient of friction would be 1. All right. That's if you've got a force of friction of 1 Newton over a weight of 1 Newton. That's on a smooth surface.
So you have this slide. No, we did.
I've written it down twice. Why I've written down twice? Have you got this one?
You got this one, yeah.
Okay, this one's better than this one. This one is nonsense. Let me delete this one. So you guys got this one?
Yeah.
Okay, so this one's a bit better. This one is showing you the relationship between the so here we've got a smooth surface, small force of friction 0.2 newtons for 1 Newton mass, and so the coefficient of friction is 0.2 because you get 0.2 per every 1 kilogram. Here we've got a rough surface, so the force of friction would be bigger. So your coefficient of friction is going to be the force of friction, which is bigger, 2 over 1. So a small coefficient of friction is on a smooth surface, and a big coefficient of friction is on a rough surface. It'll be the same. The force of friction will be slightly different, but it'll still be bigger on the rough surface than on the smooth surface. All right, or wet and dry. You guys saw yesterday that the wet surface actually gave you more friction than the dry, and that's just because of the intermolecular forces, which are probably hydrogen bonds. All right, so there's nothing for you to fill in on that slide. Yeah. So that's the friction frac which you did. Got all those values, so we don't need to discuss that. Your graphs should have looked like this. Is that kind of what they look like? Okay, great. And all you do is work out the gradient of each one, and the gradient gives you the coefficient of friction. All right.
So it wasn't a line of best fit starting from the one.
No, you just go between the dots. They should really go through 0, but they don't always. But don't worry about that.
Okay.
Now, this describes the kind of situation where you do this. What's keeping it there? But besides my finger, what's working with my finger?
The friction of the gun against the wall.
You can hear the friction when I slap off a bit and it slides. But now, which direction is friction? Up. What's down? Gravity. What's pushing in the wall? Friction. My finger. And what's pushing from the wall back towards me? Normal. So I've described that situation here. You've got a 5 kilogram mass being pushed against the wall by an applied force. You must draw the forces. That's the first thing we would ask you to do. What you're going to be doing over the right here is analyzing the situation. So friction is up, the normal force is out, and the force of gravity is down. Now you need to label those. Force of gravity, normal, and force of friction. If the thing is standing still, the force of friction must be equal to the force of gravity. So once you know the mass, it's easy to work out the force of gravity. There's stuff for you to write down there. Emma? And if it's a 5 kilogram mass, the force of gravity is 49 newtons. So in other words, the friction must be 49 newtons. But that's up, obviously. Now, what's the applied force? Well, that's going to be opposite to the normal. Now, I have to tell you what the applied force is. You can't work that out. That would depend on how much friction there is.
So what's FA?
FA is the applied force. It's opposite to the normal. So the normal and the applied force are negatives of each other. Now what we'll do is tomorrow we're going to have a look at this and analyze it a little bit further, because what happens here is this. If I ask you to work out the coefficient of friction, you just have to say, right, it's the force of friction divided by the normal. Well, in this case, it's 49, which is the force of friction, divided by the normal, which is 20, so it's 2.45. Say again? The force of friction has got to be equal to the force of gravity because it's not moving up or down. Force of gravity is just 9.8 times the mass. So that's why this is 49. Now, just the last thing you need to notice here is that the coefficient of friction definition is the force of friction over the normal. But in this case, the force of friction is given by the force of gravity, and the normal is given by the force applied. So the coefficient of friction formula is basically force of gravity over the force applied. That is opposite to the way it is when it's on a surface, on a flat surface. But I'll show you that tomorrow.